Imagine you're building a house. You wouldn't build it on sand without expecting it to sink, right? Buildings, especially large ones, need a strong foundation to stand the test of time. Just like we need solid ground to stand on, structures need something sturdy to support their weight. This is where soil-bearing capacity comes in. Soil-bearing capacity is the ability of the ground to support the weight of a building or structure without collapsing. It's a crucial factor in construction because it determines how much weight the soil can handle. If the soil is weak, the structure might sink or even collapse. Understanding soil-bearing capacity is essential for constructing safe and stable buildings. From towering skyscrapers to sprawling bridges, every structure relies on the ground beneath it. In this exploration of soil-bearing capacity, we'll uncover the methods used to determine its strength, delve into the consequences of ignoring it, and discover how this knowledge ensures the integrity and safety of our built environment. Soil-bearing capacity refers to the maximum amount of pressure a particular type of soil can withstand without experiencing excessive settlement or shear failure. In simpler terms, it's the limit of how much weight the soil can handle before it starts to give way. Think of it like this. Imagine placing a heavy object on a soft sponge. The sponge will compress and deform under the weight. However, if you place the same object on a hard surface like a table, it will remain stable. Similarly, different types of soil have varying strengths and abilities to support loads. Factors that influence soil-bearing capacity include soil type. Different soils, such as clay, sand, and silt, have different particle sizes and compositions, affecting their strength. Density. Compacted soil tends to have a higher bearing capacity than loose soil. Moisture content. Water saturation can weaken soil and reduce its load-bearing ability. Presence of organic matter. Organic matter in soil can make it more compressible, lowering its bearing capacity. Understanding these factors helps engineers and builders make informed decisions about foundation design and construction techniques to ensure the stability and safety of structures. Ignoring soil-bearing capacity can have disastrous consequences. Imagine a skyscraper, its weight carefully distributed across its foundation, built upon ground that hasn't been adequately assessed. As the building settles unevenly, cracks may appear in the walls, doors might jam, and windows might shatter. In extreme cases, the foundation could fail entirely, leading to the collapse of the entire structure. Such failures not only pose significant safety risks, but also result in substantial financial losses. By understanding and accounting for soil-bearing capacity, we can prevent such catastrophic events. Engineers can design foundations that distribute the weight of the structure effectively, ensuring that the soil below is not overloaded. Proper assessment of soil-bearing capacity is not merely a technicality, it's a fundamental aspect of responsible construction that safeguards lives and protects investments. Determining soil-bearing capacity is a critical step in the construction process. There are several methods used to assess the strength of the ground, each with its own advantages and limitations. These methods can be broadly categorized into three main types. Field tests. These tests involve conducting experiments directly on the construction site to evaluate the soil's behavior under load. Laboratory tests. Soil samples are collected from the site and analyzed in a controlled laboratory environment to determine their properties. Empirical methods. These methods rely on existing data, correlations, and formulas to estimate soil-bearing capacity based on soil characteristics and previous experience. Each of these methods provides valuable insights into the soil's ability to support loads. The choice of method depends on factors such as the size and complexity of the project, budget constraints, and the level of accuracy required. Section 5. Field tests. Putting the soil to the test. Field tests provide a direct and practical way to evaluate soil-bearing capacity at the construction site. These tests involve applying controlled loads to the soil and observing its response. One common field test is the plate load test. Plate load test. 1. Excavation. A pit is excavated to the desired depth where the foundation will be located. 2. Plate placement. A steel plate of known dimensions is placed at the bottom of the pit. 3. Load application. A hydraulic jack is used to apply incremental loads to the plate, simulating the weight of the structure. 4. Settlement measurement. The settlement of the plate under each load increment is carefully measured using dial gauges or other instruments. 5. Data analysis. The load settlement data is plotted on a graph to determine the ultimate bearing capacity of the soil, which is the load at which the settlement becomes excessive. Other field tests include the cone penetration test, also known as CPT, and the standard penetration test, or SPT. These tests provide valuable information about the soil's strength and stiffness at various depths. Section 6. Laboratory tests. A closer look. While field tests provide valuable on-site data, laboratory tests offer a more controlled and detailed analysis of soil properties. Soil samples collected from the site are subjected to various tests to determine their physical and engineering characteristics. Some common laboratory tests include direct shear test. This test measures the shear strength of the soil, which is its resistance to sliding along a plane. Triaxial compression test. This test simulates the stresses that soil experiences under load and provides information about its shear strength and compressibility. Consolidation test. This test measures the rate and amount of settlement that occurs in soil under sustained loading, providing insights into its long-term behavior. The data obtained from laboratory tests is used to calculate the soil's bearing capacity and other relevant parameters, which are then used in foundation design. Section 7. Empirical methods, using what we know. Empirical methods offer a simplified approach to estimating soil bearing capacity based on existing data, correlations, and formulas. These methods rely on the relationship between soil properties and observed bearing capacities from previous projects. One widely used empirical method is the Terzaghi bearing capacity equation. This equation considers factors such as soil cohesion, angle of internal friction, and unit weight to estimate the ultimate bearing capacity of the soil. Empirical methods are particularly useful for preliminary assessments and in situations where conducting extensive field or laboratory tests is not feasible due to time or budget constraints. However, it's important to note that these methods provide estimates, and the accuracy of the results depends on the quality and relevance of the data used. Section 8. Heavy decisions. Structures that rely on solid ground. The importance of accurately determining soil-bearing capacity is amplified when it comes to heavy construction projects. Structures that carry substantial loads, such as skyscrapers, bridges, and dams, demand meticulous attention to the ground beneath them. Skyscrapers. These towering structures exert immense pressure on the soil, requiring deep foundations and careful consideration of soil-bearing capacity to prevent settlement and ensure stability. Bridges span rivers, valleys, and other obstacles, transferring their weight and the weight of vehicles to the ground through their foundations. Accurate assessment of soil-bearing capacity is crucial for bridge design and safety. Dams hold back vast amounts of water, creating enormous pressure on their foundations. The soil beneath a dam must have sufficient bearing capacity to withstand this pressure and prevent catastrophic failures. These are just a few examples of heavy construction projects where soil-bearing capacity plays a critical role. By understanding the principles of soil mechanics and employing appropriate testing and design methods, engineers can ensure the safety and longevity of these impressive feats of engineering. Section 9. Conclusion. Building on a strong foundation. Soil-bearing capacity is the unsung hero of construction, the silent guardian that ensures the stability and safety of our built environment. From the tallest skyscrapers to the longest bridges, every structure relies on the ground beneath it to support its weight. Ignoring soil-bearing capacity is akin to building a house on sand, a recipe for disaster. By understanding the factors that influence soil-bearing capacity, employing appropriate testing methods, and incorporating sound engineering principles, we can construct structures that stand the test of time. Accurate assessment of soil-bearing capacity is not just a technicality, it's a fundamental aspect of responsible construction that protects lives, safeguards investments, and ensures the integrity of our infrastructure. As we continue to push the boundaries of engineering and architecture, the importance of soil-bearing capacity will only become more pronounced. By building on a strong foundation of knowledge and meticulous analysis, we can create a built environment that is both awe-inspiring and enduring.